All right, so here's an angle. Oops, I forgot to put the angle in the diagram. There we go, theta. And I drew the same diagram from the definition of sine and cosine, so we know that sine here is v over r, and cosine is u over r by definition. Whatever u, v, and r happens to be for this angle, for whatever diagram you draw. The one thing that we did last time is that to just say, well, okay, so if I wanted to find a sine and cosine of an angle, it doesn't really matter how big a triangle I draw because the when you divide the ratio, then it cancels out whatever size you have, and ultimately it gives you the same answer. So we went, oh, why don't we make R1? Why don't we make this hypotenuse 1? So when you do the division down in sine and cosine, you get just v and u. You don't have to go and say, oh man, I have to divide by, square root of whatever, which isn't too bad, but, if you don't have to, why do it? So when we do that, you get a really cool thing called a unit circle, which you probably expected because it's the title of the video and the thing that was written on top. All right. Remember, the unit circle is a circle that has a radius of 1. And so every point that has a hypotenuse of 1 really, or well, I shouldn't say hypotenuse, but a distance of 1 from the origin really is on the unit circle. So no matter where I draw the point, if it's 1 away, well, it's got to be on this unit circle. Right? There we go. I'm not going to draw anymore. You get the idea. And so the whole idea of trigonometry, kind of figuring out sines and cosines of all these angles, so like here's an angle, here's another angle, and then there are a bunch of other angles that I'm not going to draw in. The idea of analyzing these coordinates, these points that are given by the angles, if your radius of your hypotenuse is 1, then it's really analyzing points on this unit circle. So let's do that. So right here, I have a GeoGebra interactive demonstration thing about a unit circle. So this circle right here has a radius of 1. Then you can see that because the coordinate system is kind of underneath that. And then here's an angle. Right now it's 43.56 degrees. And then this is, I should say, the positive x-axis, sorry, and this line segment here forms the angle which GeoGebra called alpha here, right? And then we have this red segment over here and a blue segment down here, and this one is sort of the opposite, and this one's the adjacent side, right? Because we have an acute angle, it's a nice acute triangle. We don't have any negative sides or coordinates or whatever. It's all nice and happy. And as I move this point around, the angle changes, and you can see that the lengths of the red and blue lines change. The opposites and adjacent change, which shouldn't be a surprise, right? Change the angle, you change the sides, duh. And over here on the right, are the numerical values of the vertical coordinate or the v coordinate of this point over here, and the horizontal coordinate or the u coordinate of this point. So if I move this, you can see those numbers change just like the lengths change. Okay, now I'm still kind of in the first quadrant. I'm afraid to leave it, I guess. Before we move to the other quadrants, remember that this length is 1, the hypotenuse is 1. So the vertical coordinate is really the sine of the angle right now, 39 degrees. Because remember that to get the sine of the angle alpha, we divide the vertical coordinate, the v coordinate, by the hypotenuse, which is 1. So 0.63 over 1, still 0.63. And same thing with the horizontal coordinate. This 0.78 here, that's the cosine. So right now they're labeled as vertical coordinate and horizontal coordinate, but you can really think of them as sine and cosine if you want to. And we want to really do that later. anyway, so maybe it's good practice. Anyway, let me start moving this point around. Bigger angle. Notice that the vertical coordinate's going up because, well, the point's going up, right? It's going higher as the angle becomes bigger. 90 degrees. Vertical coordinates 1, horizontal coordinates 0. That means the sine of the 90 degrees is 1 over 1, and the cosine is 0 over 1. And it's kind of weird because you're like, wait a second, 0 cosine? I mean, like, cosine's adjacent over hypotenuse, right? And you can't have 0 side. That doesn't make sense. But if you look at this picture here, right? You see there's the blue line, that's the quote-unquote adjacent side to the angle. As soon as this thing snaps to 90 degrees, poof, the blue side's gone. When you have a 90-degree angle, the diagram kind of collapses on itself. And that's where the 0 really comes from geometrically, because there's no blue line, so there's no adjacent is 0. And once I move beyond the crazy 90-degree thing, there's an adjacent blue side again. But now, notice that the blue line is on the left. Now over here, it's still saying positive 0.84. That's because we're using GeoGebra, not algebra. Right? GeoGebra is still thinking in geometry, so it's still measuring the length of the blue line. But you got to remember that the blue line now represents a negative coordinate. So the cosine here of 144.96 degrees, which I happen to stop at, the cosine is actually negative 0.82, not 0.82, while the sine is still positive 0.57. Then we keep going, and now, poof, no red line, so no sine. Sine's 0, while cosine is negative 1, because remember, blue line's pointing to the left. And now we move down over here, vertical coordinates at negative 1 actually, because remember GeoGebra is still thinking in lengths, but in the coordinate system, the red line now represents a negative coordinate in the third quadrant and later in the fourth quadrant. And then over here, we have still a negative vertical coordinate, but a positive horizontal coordinate, and now all the way back to 0 degrees, or 360 degrees, whatever you want to call it. And when you have 360 or 0 degrees, notice that the vertical coordinate's 0. There's no opposite side. It collapses. And so the sine is 1. And the cosine, the sine is 0, no opposite. And the cosine is 0. And I'm going to kind of just rotate this at a higher speed. And you can just see that these lines, the red and blue lines, expand and then contract and then expand again in the other direction and contract again. So it's kind of, if we look at just the red line over here, starting from 0, it gets longer and longer and longer until it gets to its maximum length of 1. The red line is now at 1. And now it gets shorter, down to 0. And now remember, the red line represents a negative number, so we're getting even more negative until it gets to the bottom at negative 1, and then it goes back up again at 1. And you can do the same thing with the blue line. It goes from 1 down to 0, down to negative 1, because left is negative for the blue, and then going back up to 0, and then up to 1. And it keeps going and going and going, because it's a circle, and circles can go on forever. But I'm going to stop talking about this now and come back to this other thing where we can list the important facts we just learned by looking at a unit circle. So here's the thing, right? We did the unit circle, it's nice and pretty, but what are the important things? Well, number one, the one thing we learned is that sine of 0 degrees is 0. Remember, that's when the opposite side collapses, and cosine of 0 degrees is 1. And then sine of 90 degrees is 1, while cosine of 90 degrees is 0. Sine of 180 degrees is 0. and cosine of 180 degrees is -1. If you don't remember this, you can go back, I guess, rewind and play it in slow motion or something. Sine of 270 is -1, and then cosine of 270 is 0, and sine of 360 is 0, and cosine of 360 is 1. Right, so this is sort of one cycle of sine and cosine. Start from 0 degrees to 360 degrees. You get the cycle going from, for sine, 0 up to 1, down to 0, down to -1, up to 0 again. And for cosine, it's you go down first and then you go up. Let's graph this, or let's graph these. So I'm going to draw a nice set of axes, -1 and +1. And this is 360 degrees. Oops, forgot the 0. 180 is halfway, 90 is here, and then 270 is here. And now remember that sine of 0 degrees is 0, so let's put these points down. Sine of 0 is 0, sine of 90 is 1, 180 is 0, and then 270 gives you -1, 360 gives you 0 again. So we kind of have this wave thing going on, right? It goes up and then down and then up. And I'm going to collect these. Now, you may be wondering, wait a second, why is it like a wave? Why isn't it linear? Well, we haven't really plotted all the other points yet, so it could be linear. I mean, it makes sense. But if we go back to the unit circle, which is right here, you'll notice that, let's start right here again, right? The red line doesn't really go up in a linear fashion, right? Or the length doesn't increase in a linear fashion. Because right here, it kind of starts from nothing and it kind of goes up goes to like, 0.4 pretty quickly. But by the time it reaches 0.9 right here, it's only 66 degrees. It's gonna still take another 30 degrees before it gets to 1.0. So this whole idea of linear, the whole linear thing would mean that if the function was linear, it would mean that the length of this red line was increasing at a constant rate, right? It's going up whatever the slope is, unit at a time. But it's not. It's actually changing. It's slowing down. So if you look back here at this graph, actually the sine or the red line increases right here. Right here increases pretty steeply and then kind of levels off. And then it does other things, which we'll talk about later. So it's not linear. It's not exactly a parabola. We'll examine the shape a little more closely in the near future. But this is essentially what, oops, forgot my axes. Y equals sine of theta looks like. Let's draw cosine. I'm going to plot those 5 points we have down. And look at that. That's y equals cosine theta. Yet another wave. In fact, we call these waves, right? Because they look like waves. And, up and down, up and down, up and down. Let's do the wave. Okay. These are the graphs of the sine and cosine functions, and we really got them just by playing with the unit circle. It's not really hard. It's really good to remember generally what they look like. These values are really useful to commit to memory. They're also 30 and 60 and 45 degrees and whatever. Those are important too, but these, as far as we're concerned with the unit circle, are essentially the most important values. They're the ones that kind of section off sine and cosine into the quadrants. Speaking of quadrants, let's go back to the GeoGebra file. Notice that here red and blue are both pointing positive directions, right and up. Here red's up, so sine's still positive, but now blue's negative because it's pointing to the left, so that means cosine's negative. Now here, both of them are pointing left/down, so they're negative. And here, the cosine, the blue, is pointing to the right, so it's positive. And the red one, sine, it's negative because it's pointing down. And back here in quadrant 1, they're both positive again. So fact number 2, I guess, fact category number 2, because there were a lot of facts in number 1, is that if you draw the 4 quadrants, if you draw the coordinate system, in the first quadrant, sine theta and cosine theta are both positive. In the second quadrant, since sine corresponds to the vertical axis, it's still positive because you're still on top. But now cosine is negative because you're to the left of the origin. And cosine, remember, is the first coordinate, the u coordinate. All right, let me label my axes. Now you're in the third quadrant, both coordinates are negative. And in the fourth quadrant, sine, which is the vertical coordinate, is negative, but cosine is totally positive. And so you can remember, if you remember the example we did, and if you remember problems you did where you used a reference angle to find sides of triangles or coordinates in order to find the sine and cosine of an angle, and you notice that sometimes the sine and cosine is the same, sometimes the signs have changed, S-I-G-N-S, not S-I-N-E-S. Sometimes the positive, negative stuff changes. Well, it's because you're in a different quadrant, right? For a reference angle, sine and cosine are always positive because the reference angle by definition is an acute angle. So if you draw it in standard position, it would be in the first quadrant. And so one really quick way of finding sines and cosines of any angle is to find a sine and cosine of its reference angle, which are both positive, and then figure out which quadrant you're in. Or rather, by you're in, I mean the angle you want is in, and then just change the sign. So let's do an example. Let's do a quick example. Let's see if we can find a sine of 300 degrees. Let's draw the angle. 300 degrees would be something like this, right? The total is 360, so this is 300 degrees. And then the reference angle, theta ref, would be 60 degrees because you have 300, you need 60 more to get back to the x-axis, or the u-axis, I guess. Let me label my axes again. I keep forgetting. I'm sorry. The reference angle, 60 degrees, well, what's the sine of 60 degrees? You can draw a triangle, use a calculator, look it up, but I'm just going to do it from memory. It's root 3 over 2. And, well, okay, that's great. That's the sine of 60 degrees. But what's the sine of 300 degrees? Well, let's look at this chart. We're in the fourth quadrant now. So we're right here. Sine's negative. So that means we basically just need to make this negative. Sine of 360 degrees is negative root 3 over 2. And when you think about it, you know, it's kind of like witchcraft. You're like, ooh, let's change the sign and everything is all right. Well, let me draw this in purple. This line is sort of the opposite of it's the opposite side of the 60-degree reference angle, and it represents the sine measure of 60 degrees and simultaneously 300 degrees. Because the 60-degree angle is here, so that's the opposite side. And so when we look at the 60 degrees, we're kind of looking at this thing upside down. So remembering that for an acute angle, sine and cosine are both positive, you know, we're really looking at this purple line as just a length. But for 300 degrees, we're looking at this purple line as a vertical coordinate. So the purple line gives us this v coordinate. In fact, its length gives us the v coordinate, except we have to negate its length because this line goes down from the u-axis, from the horizontal axis. So it makes sense that these numbers, or if you want to think about it more mathematically, the absolute values of sine 60 and sine 300 are the same, but the positive negativeness, the sign sign is different.